Good morning, folks. It's logical morning. I know it's good. It's really afternoon, but good morning. Lab 1 report is due a week after you do the demo. So you're doing the demo for Lab 1 next week, except for the few of you who have finished already. And then a week after that, the report is due as explained on the slightly cryptic but very complete chart here. So week 2, we're in Lab 1, week 1 right now. Next week we're in Lab 1, week 2. The next week will be Lab 2, week 1, lab report due, and homework 2. Any questions about timing? Yes.
So it's due 7 days from your demo or from when you were supposed to demo?
It's due 7 days from your scheduled week 2 lab.
All right.
So if your lab's on Tuesday, it's due on Tuesday. If your lab's on Friday, it's due on Friday.
So if you demo early, you have more time to do the report.
If you do demo early, it is still due 7 days after week 2.
All right.
If you demo early, you get done early, you still have to come to lab. Lab is not optional. You can start on the next lab exercise. You can start working on final projects, but you have to come to lab. I saw a couple of really odd faults yesterday. One group had a board that had worked. They had programmed it. They loaned their TFT to somebody. Uh-oh. Put it back in the board. The board didn't program. The TFT worked. The board didn't program. What in the heck is going on? We took everything off that board, the programmer, the cable, everything else, and it turned out that what was going on was when they had plugged the TFT back in, they'd pushed it down a little bit, and the back of the TFT had shorted against the one capacitor on the service mount capacitor and shorted that capacitor to ground. You lift it up a millimeter, it all works. So folks, I have a foam plastic ESD material that exactly spaces correctly under the TFT. If you'd like to put a small brace under it of plastic foam, I suggest it's a good idea. That also makes it mechanically more stable when you accidentally lean on it. So we can set that up anytime. Just let me know and I'll cut off a piece for you. One group, I didn't even know you could do this, but I learn stuff from students all the time. One group figured out that it is possible to route Ivref to the analog to digital converter. So you can use the ADC to measure Ivref. That's cool. I think most people, though, are connecting a variable voltage to the input of the comparator and getting a transition voltage, which is just as good. But I really like these little tidbits of information because it's yet another way of using the hardware toolkit on the chip to solve an interesting problem. Any more questions about Lab 1? Yes?
While I was looking on the policy page, it gives some examples for lab reports, but 2 out of the 3 links are broken.
I believe they're now fixed. Well, you looked yesterday and they were broken?
Yeah.
Because I fixed them last week. But if you have a cached copy, because you looked at it once before on time, then you won't get the current version. Let me see if I can find that. Where did I put the policy page? Policy. Down towards the end is indeed a section on lab reports, and the example report.
That's broken. The first and second one.
I think it's fixed. I just opened it.
You may have to force reload the page.
Okay.
Control Shift Stand on Head Reload. It is fixed, right? You said you got it. Somebody got it.
Yeah.
All right.
I just tried to reload the page and it didn't work for me, but I tried to click on it before.
I'll check it.
Okay.
Anyway, the third one works.
Yeah, the third one.
Somebody reported that last week, and I was pretty sure I'd fixed it. I tested it even.
No, I think the third one.
Aha! I wonder if I have a bogus copy of the policy page laying around someplace. Maybe I better check that and make sure there aren't two copies floating around. Anything else on Lab 1? Yes.
So if you're measuring the Ivref with your own ADC, what are you comparing it against? Measuring your own internal reference versus what? Your own internal reference?
So, good question. If you're measuring Ivref versus the ADC, then the default reference voltage for the ADC is VDD. And so it is ratiometric with respect to VDD. So you're going to get a count between 0 and 1023, and the correct way to interpret that is as a fraction over 1024 times VDD is the actual voltage. So it's a number between 0 and 1023 over 1024 times VDD.
Do you divide by 1023 or 1024?
Does it matter? It's 1 part in 1,000.
Okay.
The ADC isn't that accurate. It doesn't matter.
I have another question.
Yeah.
Completely unrelated. So if I'm running my timer capture and I'm getting different results, like 30 cycles different, on the same capacitor.
So you're running the same capacitor and you're getting a jitter of like 4,430, 4,420, 440, that kind of variation in the third place, more or less. So my guess is that there is a small amount of noise from any number of different sources imposed on the analog signal from the capacitor. After all, there's an SPI clock running for the TFT. It's within a centimeter or two of your capacitor, or a few centimeters. It may be inducing fairly large high-frequency noise into the comparator lead. It's in the third place. It only takes 1% noise to change that by 30 counts if it's in the 4,000s. And I don't even think you'll see 1% noise on the oscilloscope. How to get around that? Well, you could assume that it's normally distributed and take the mean of 10 readings. And how much better will that make the approximation? Square root of 10 better. About 3.2 better. Factor of 3.2 better. Something like that. So maybe measuring 10 times makes sense. Measuring 100 times probably doesn't. Anything else on Lab 1? Let's start on lab 2. It being 1 week from the start of, actually it's only 5 days from the start of lab 2 now. Because lab 2 starts for the Tuesday people on Wednesday. Oh yes, remember that Monday is a holiday. No class. No services. No offices open. Create a call generator. So what I'm going to ask you to do is to specify a cricket call using a numeric keypad, which you'll have to program up, and to extract from the numeric keypad about 5 parameters. And real calls can be quite complex, but we're going to abstract away almost the simplest calls. A call is made up by indefinitely repeating a chirp. A chirp is made up of a certain number of syllables. A syllable is made up of a sine wave burst. So what you're going to get is structured groups of bursts of sine waves. So a chirp is going to be a group of sine waves, a burst of sine waves, here 4 bursts. Then there's a chirp repeat interval, then it starts over again. The syllables are sine wave bursts. I wrote a little MATLAB program here which does this in not real time. So an individual syllable in my simple code looks like this. You have a sine wave that ramps up over about 4 or 5 milliseconds, stays high, and then ramps down. And the ramping is necessary, particularly for short bursts, because if you were to merely turn on a sine wave at full power and then turn it off again, you can treat this, remember now, we're going back to a little bit of signal theory here. You could treat this as a sine wave modulated by a square wave. It's gated by a square wave, and the Fourier components of the square wave will appear in the output. That is to say, there will be a very broadband signal that appears in the output, which you can hear. And the effect will be, this will click in the most brutal fashion. So instead of hearing a tone burst, all you hear is click, 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 click. So, particularly for short bursts, and in fact, as required in this lab for all bursts, for all syllables, you have to ramp up the sine wave and then ramp it back down again. And there's going to be a specification for duration on the sine wave burst that has to be accurate within a millisecond. The ramp up and ramp down are 5 milliseconds or 4 milliseconds each. So where do you start measuring the length of the burst? It doesn't make sense to start here and stop here because there's no energy here. All right, there's no energy there. It doesn't make sense to stop here because that's almost full energy. So let's say half. So the length of the burst that is specified in the lab will be from half amplitude to half amplitude. Now we're going to concatenate together a bunch of those to make a syllable. So this is now 4 sine wave bursts, each one ramped up and ramped down. Then those bursts are going to be concatenated into chirps so that the whole song looks like something like this. And it's very pleasing. The whole lab sounds like summer crickets. TAs love it. The MATLAB program, of course, generates the whole vector and then plays it. You're going to be generating one sample at a time and playing it in real time, continuously, forever. So you're not going to synthesize a second of sound. What you're going to do in this lab is you're going to calculate the next sample and play it. And then 1/44,000th of a second later, you're going to calculate the next sample and play it. And the output is going to be through that DAC on your board. You know, the digital to analog converter that we tested. You're going to be using we'll talk more about this, a serial peripheral interface connected DAC to produce 12-bit accuracy reproductions of the sine wave bursts, which will then be fed into speakers. We have to talk quite a lot about how to scan a keypad. So we're going to need to talk about keypad. We need to talk about serial peripheral interface. And we need to talk about how we're going to generate a sine wave. Because at 44 kilohertz, you don't have time to calculate sine theta. In fact, why would you do that? Because it's a highly repetitive function. Why not just store a table and go through the table? So what we're going to, the method we're going to use for producing sine waves is called direct digital synthesis. It is a process for defining one sine wave table and then stepping through it at different rates to make different output frequencies. And I'm going to talk a lot about DDS because there's something hard about it. I don't know what's hard about it. But this is a occupational hazard of teaching the same material for 20 years in a row. Why could this possibly be hard? I've done it 20 times, right? So there's something about it that's difficult, and I don't quite understand what it is, but we'll go through it a bunch of different ways and see what you think. So what do we start with? So the keypad then is going to input parameters, a chirp repeat interval, the number of syllables, syllable durations, syllable repeat interval, and the burst frequency. It is possible, it is possible to put in a set of parameters which is impossible. Let's say that the number of syllables times the syllable duration is greater than the chirp repeat interval. So you're going to have to do some error checking on the inputs to make sure you can actually synthesize the song. And I do not mean to imply by putting up 5 songs that you can press a button between 1 and 5 and play those songs and pass the lab. What I mean is you're going to be able to enter any chirp repeat interval, any number of syllables, any syllable duration, and get a song out if it's possible. So you have to make a parameter parser, you have to figure out a way of making a hierarchical timing setup. It's really an exercise about time, handling time. The high speed synthesis necessary for the audio, and the low speed time control to do all of the duration intervals correctly. Any questions on this? So, the keypads we have, let's start with keypads. So the keypads we have are explained in TFT and keypad page. The keypads are laid out as a as a 3x4 array of numerals and special characters. 1, 2, 3, 4, 5, 6, 7, 8, 9. What is it? Star 0 pound. It's the familiar telephone keypad layout. And as we can see from the schematic, what each of the keys actually is a switch that shorts one row wire to one column wire. So it is a matrix of switches, each of which shorts one row wire. So pushing the 8 button shorts the A2 row wire to the B8 column wire. And what we want to do is, the first step we need to do to understand the keyboard is to figure out how we're going to scan the keyboard to find out which button was pushed. And find out if more than one button was pushed, because that should throw an error. There's a bunch of different ways to do this. I decided to do it in a fairly simple fashion, in which the row lines were raised to a logic true. I'm going to say this a bunch of times, so don't need to write anything down right now. The row line A0 is raised to logic true, while all the rest of A1 through A3 are at logic 0. And then you see if B7, B8, or B9, any of those are high. Then you do the same thing for A1 and check B7, B8, and B9 again. And if you raise one at a time and check all 3 lines, you have complete information. You can tell exactly which button was pushed and if more than one was pushed. And when there's more or less clever ways of doing this, and I'll show you one way that is not particularly clever, but it's easy to code. There is one small problem, and that is these are mechanical switches. They are spring mass systems. There's a spring in there that returns the switch. Since it is a spring mass system, it oscillates. Oh man, it oscillates. So, you push a button, let's say you push the button here. What you would expect is that if we had VDD across the switch, that VDD would appear at the output in some waveform that looked like this. In fact, what happens is something like that. The switch may oscillate several times before it finally settles in. And this whole distance here, this whole length of time, is perhaps, 5 milliseconds or so. You say, who cares, right? I pushed a button, it went down. But if this was your cell phone, and you were dialing 911, and you pressed the 9 and got 5 nines, yeah, you'd throw the thing in the trash and yell for help, right? So the oscillation matters, and you are going to have to build, I'll talk about this in great detail, you're going to have to build a debounce state machine to decide whether or not a bounce is a valid push or just part of a larger sequence. So the first thing we're going to do is figure out how to crudely scan the keyboard to see if a switch is closed or open. Then we're going to take that routine that we write and call it from a state machine that checks several times to see what is actually bouncing. Once we find out that it's not bouncing anymore and is a valid key press, then the state machine is going to have to build a string which represents a number, a parameter number, and then use that in a calculation. So we're going to drive, for instance, we're going to now abstract away the keyboard into just the wires, understanding that there is a button at each point. A0, A1, A2, A3, B7. These are bit numbers in the port actually, B8, B9. We're going to drive A0 high, then A1, then A2, then A3, and at every point we're going to read B7, B8, and B9. Why are these resistors here? Well, I guess to understand that you have to see what they're actually connected to, which is cut off at the bottom. Oh, they go to ground. Okay. So these 10K resistors go to ground. Why are they there? Again? Yeah, in protection in a sense, yes. They're pull downs because when the button is not pushed, the switch is disconnected, and that means those I/O ports are floating and have an undefined voltage unless you pull them down. So these are pull down resistors to keep the ports from floating when the switch is open. When I did this diagram, I didn't yet know how to turn on the internal pull downs. There are internal pull downs on the chip. You don't have to have external resistors, but you have to have some resistance. You either have to turn on the internal pull downs or use 3 10K resistors, 1 per line. Why are there 300 ohm resistors on the drive ports, on the outputs, the A1 through A3 outputs? This is slightly more obscure.
First 2 buttons on the same time that cover 2 rows. You'd be shorting those nests together.
Exactly. If you, let's say you pressed 1 and 4 at the same time, you bring A0 high. If there were no 300 ohm resistors here, you'd bring A0 high, and that would be shorted to A1, which is low, and one of the output transistors would fail permanently. So the 300 ohm resistors protect the output ports from each other. There's other ways of doing this which might be cleaner. Anybody know of them? Know what to do to isolate ports? Using a nonlinear device. diode. But 300 ohm resistors work. There's another side effect that they have in terms of error control. If you press two buttons vertically, because the two 300 ohm resistors act as a voltage divider, the node never goes to logic high and it disregards the double push. So I'm using the flaky electronic aspect of this as an error control for double pushing buttons. I didn't actually design that in. After I built it, I tested it and it worked. So I can't really take any credit for it at all. So what we're going to do when we're going to put this series of pulses in, A0, then A1, then A2, then A3. And we're going to look at B7, B8, and B9. And we're going to make a scan code which concatenates, it actually ORs together, the two lower bits of A and 3 middle bits of the B port to produce a unique code depending on which switch is closed. So what we're going to do in code is we're going to, let's see, if row 1 is driven, let's see. So row 1 is driven, we're going to have a 1 in the A register. If row 2 is driven, we'll have a 2. We'll have the second bit. Otherwise, we'll have 1. A1 high, A2 by, so it'll be 1, 2, 4, 8. It will be the value of the A register. And with looking at the output will either be, for valid pushes, will either be B7, which is 0x80, B8, which is 0x100, or B9, which is 0x200. So the B port, when read, will be one of 80, 11, 100, or 200. We're going to concatenate that with 4 lower bits and build a unique scan code. Or 2 lower bits and build a unique scan code. Yes?
Is this like supposed to happen through like interrupts or through event capture?
I don't see any reason to use interrupts because humans are so slow. And it's not like, I mean, if we were powering the system down and we wanted to sit there not doing anything until we press a button, then an interrupt would be a reasonable thing to do. But given that the system is going to be doing synthesis all of the time, and under high power, there's nothing particularly to be gained by putting it to sleep and waiting for an interrupt. So we're just going to scan in the, we're going to poll the bits. We have a thread that sits there and polls the keypad continuously, and the humans are so slow that there's no load on the thread at all. The thread's going to spend 98% of its time sleeping. So we OR together the bits that we read from B and the bits that we drive from A. So what happens if we push a 1? We push a 1. Then this switch is closed. That's column B7, row 0. So the scan code for a 1 then would be 0x81. Right? If we press a 5, then the scan code will be anyone? What's the first digit? 1, O, of course, and then 2. A star is here. It's 4th row, so that's an 8. That's the third bit is an 8. And first column, so a star then would be 0x 208, but wait, 2 is B9, right? And a star is in the first column. So it should be 88. So this column is 0x200, this column is 0x100, this column is 0x80. This row is 0 x 0x01, 0x02, 0x04, 0x08. So we press a button, we get a scan code out. Then what we need to do is a table lookup, which converts the scan code into a useful output. In other words, it converts the scan code into an integer or a command symbol, pound or star. And we're going to arrange the table so that the index of the table which is returned as a hit gives us the actual integer digit. I think, though, I better stop, because when we start talking about the code, it's more than 10 minutes. And we have a visitor, David Winkler, who would like to tell you about a possible project that spans biology and electrical engineering and who knows what else, communication and all kinds of stuff.
Yeah. Thanks, Bruce. I see a few familiar faces. You guys know that, a few people know that I'm a biologist I'm not an engineer at all. But I love working with engineers because for many years we've been taking things that we design in the lab here and put them on birds' backs and then take them out into nature. So my job is I'm a biologist or ornithologist, and so I'm here to convince you that doing neat ECE projects that have feathers on them is cooler than ECE projects without feathers. So how do I go forward here, Bruce?
So this is a PDF, so I think you're just going to scroll down.
Okay. So to give you an idea of the kinds of things we do, we've been really pushing hard on the really small end of the spectrum. I have plans to build these big fancy satellite tags that have GPS and 3D accelerometry, and they talk to the cell phone network, and those are wonderful tags, but they weigh about 3 or 4 times what the birds weigh that I work on. And birds usually can't carry more than about 4% of their mass, and my birds are 20 grams, and there are a lot of birds that are smaller. So we have a sort of a 1 gram ceiling for things that we want to develop, and we usually are much happier if we get down to like 0.4 of a gram. So that means that our biggest innovation so far has been to go totally solar. A lot of the tag mass that you see out there in wildlife tags today is the battery. And to avoid that, we've developed circuits that basically are just charging a capacitor and discharging with a radio transmission whenever the capacitor is charged. So we're really interested in taking that further. We are going to use that same circuit, and we're making a tag right now that will be even much smaller without the circuitry associated with solar power, with a tiny battery, but it won't last very long. But that's a tag that we're developing for mice. And the way we will deal with that is we'll be inductively charging the tag every time the mouse goes to its nest at night. So what we are doing on the tags without batteries is trying to push forward and see how much we can get done without batteries. It involves inevitably some more capacitors or some other ways of storing charge. But the three main things we're working on right now are a solar geolocating tag. That is a tag that records time-stamped light levels around twilight every day for a year or two. And when it comes into range of an interrogating receiver that's constantly sending out a beacon saying, hey, here I am, I want your data, it coughs up the data. It might take a few seconds to transmit all those data. And from those data, we can then reconstruct where the bird has been for the last year or two. That's a tag we're in late stages of developing. We hope to have it done by next spring. We're looking for both undergrads and for MN students who might be interested in that tag. A new tag that we've just got a grant to work on is a tag that identifies different species of mosquitoes that are coming to feed on birds at night. And it turns out that each mosquito has a distinctive wing beat frequency, the sound it makes, that whine it makes. They make different whines, and each of them carries different parasites. So it's very very important to know which mosquitoes are potentially infecting birds and, by extension, a lot of other things like humans. And so we're starting to work on that tag right now, and anybody who's really interested in the interaction with acoustics and really small circuitry, I'd encourage you to get in touch about that. We also have heart rate, acceleration, altitude, and chemical sensing tags that we've built in the past, and we're working on all of those in sort of battery-free versions. So if any of this sounds interesting, please get in touch. We also do a lot of work with our base stations, are Raspberry Pi based, and there are a couple of big issues with Raspberry Pis when you put them out in the environment and leave them on their own. We need some new software improvements to communicate with each new tag. Each one of these new tags will need some manipulation of the base station hardware, not too much. We're also working on a direction finding receiver that would use dual antennas and look at phase differences to actually look at the direction that these very short pulses from the tags are coming. And if you put those in a networked array, you can soon do localization in a very nicely scalable way. And the thing I started talking about with the Raspberry Pis is one of the biggest problems is that they're not very good about how they deal with running out of power. And when they go down, they tend to go down in flames and with a lot of damage to the files in them. And so we are really interested in developing something that Fred here last year started working on, which we're going to make into like a watchdog to run with a Pi, so that if the voltage in the batteries is starting to go down, it can gracefully store everything before shutting down and waiting for some more power. So these are the kinds of things we do, and these are what the tags look like when they're deployed. These are tags on some swallows. These are little 20-gram birds here in Ithaca. You can't see it here, but there's a swallow flying by here with just a little tiny antenna trailing behind. And these are tags that we've developed for Sanderlings. They have to be developed in a very different kind of package. They're going onto a custom 3D printed harness that holds the tag on the bird for the rest of its life. So anyway, that's what we do. There is Eli funding available. I also have grant funding available if you guys need money. If you need credits, that could be arranged too. But I'm looking for anybody with an interest in these kinds of projects. And we have a lot of experience dealing with both undergrads and MN students and getting them productively hooked up with things. The big difference between what we do and what a project team does is that we're actually producing product that's going out there into the real world rather than competing on some rules that somebody else made up across the country.
If I can insert, a a final project in this course could be part of Tabor.
Yeah, that would be awesome.
And the rules for final projects, if you look at them yet, you will, say that if you are dealing with an outside funded research unit, we completely waive the budget. You can spend whatever you want. And that's to encourage collaboration, because sometimes external systems will have a big expensive piece that has to be integrated into your small cheap piece, but it has to work all together. Secondly, these make great MEng projects, folks, because you're part of a larger team with a well-defined goal.
And a lot of engineers really get a kick out of knowing that the stuff they designed is now flying around out there doing science.
And you occasionally hire MEngs after they graduate, right?
Yeah, we're always looking for people who really get this in their blood.
Okay. Any questions on that? Consider. Interesting stuff. Birds are fun.
I'm going to leave a few of my cards out here. If you're interested, please pick them up. And if we run out, let Bruce know. All right.
All right.
Thanks a lot, Bruce.
Thank
for
you.
the time, and look forward to meeting some of you.
Okay. I'm going to open up lab as soon as I get lunch microwaved up.